Hello everyone, here we'll be discussing chapter 3.7, which is a discussion on rate of change in the natural and social sciences. In reality, we'll just be talking about rate of change, and we'll see some examples that may dip into these topics here. Like for instance, we see this example in physics, which is a natural science. We may see an example in biology, and we may maybe do an example of something in economics, which has to do with cost and profit functions basically. And revenue to it, I suppose. But we'll see that in due time. Now, first I want to recall this. The derivative dy over dx is the limit as delta x goes to 0 of delta y over delta x. In fact, if we haven't seen it written like this before, because I don't think I've shown it like this really kind of shows where the notation for Leibniz notation comes from. Notice that delta, Greek letter delta, is turned into the Roman letters d. Delta starts with d, so that makes sense. And notice this way of writing it is different than the definition of derivative, but this is a valid expression for derivative. It's just the limit as the denominator goes to 0 of the of the slope of the secant line, which is just a change in y over the change in x. Awesome. And this is the instantaneous rate of change of y with respect to x. So the numerator difference over the denominator difference, or numerator variable over the denominator difference. All right. So now, for this example, we're going to be talking about something that we kind of seen before in, I guess, way in chapter 2, where we started talking about derivatives and tangent lines, and we saw that there was a relationship to physics, obviously. Basically, the slope of the tangent line is the instantaneous velocity, and that's kind of all we saw, really. But we're going to go a little further here. We're going to try to analyze some things. I don't really give us too much space here, so in fact, maybe in red I can write the answers, but let's see. So first off, notice we're given this position of a particle given by this function, s of t is equal to t cubed minus 6t plus 9t, and we're asked these 5 questions. So A asks us to find the velocity at time t. So notice I kind of said earlier, velocity, if you don't know, is just the change, the rate of change of distance with respect to time. And notice here, instantaneous rate of change of y with respect to x. So it's dy over dx. So here, if this is s, that's our distance, then velocity is just, well, ds over dt, because it's the change of, the rate of change of distance over time, is how fast your distance is changing, basically. So really, this is just ds over dt, or let's write it as s prime of t. And that's super simple to find given an expression like this. Just use the power rule on each term. You get 3t squared minus 12t plus 9. Fantastic. And now B asks us what is the velocity after 2 seconds and after 4 seconds. This is also pretty simple given that we know A, because to answer the first one, this is just s prime of 2. So you plug in 2. Notice here you'll get, well, 3 times 2 squared, that's 3 times 4 is 12. 12 times 2 is 24. 12 minus 24 is negative 12. And negative 12 plus 9 is negative 3. It's negative 3. I wonder if we're actually given units here. Yeah, sorry. So I didn't write it, but actually S is measured in meters. So here the unit is going to be meters per second. And then similarly for 4 seconds, we plug in 4. So I think we have space for that. Notice that's just S prime of 4. And when you plug in 4 here, you get, well, let's see. 4 squared is 16, 3 times that's 48. And 12 times 4 is also 48, as it turns out. Good, so those cancel out and you just get 9 meters per second. So let me squeeze that in, hope we can see that. And we can kind of see, let me tilt the camera a little bit so you can see it more clearly. There we go, it's fine. So now part C asks, when is a particle at rest? So remember, something is at rest when it has no velocity, and we have an equation for the velocity, s prime of t. So really what we want to do is set that equal to 0, and I'll do that below. So at rest, you set the velocity s prime of t equal to 0. So notice that just gives us 3t squared minus 12t plus 9 is equal to 0. And we'll solve this equation by factoring. Notice first they all have 3 in common. So we'll factor the 3 out by dividing everything by 3. And then we'll notice that we can actually factor this trinomial. We're looking for two numbers and multiply to 3 and add to negative 4. So that's negative 1 and negative 3. And then solving this equation just gives us the times t equals +1 and +3. Because notice this 3 in front doesn't amount to anything. You just divide by 3 and that's fine. But t minus 1 and t minus 3 you can't really divide by because they're possibly 0. When t minus 1 is 0, t is 1. When t minus 3 is 0, t is 3. So this expression is only 0 when t is either of these things. The 3 is kind of negligible in some sense. But anyways. So when is it at rest? It is at rest at 1 second and at 3 seconds. Okay. When is a particle moving in the positive direction? Well, actually, when something's moving in the positive direction, its velocity is positive, otherwise its velocity is negative. So in fact, in part B, after 2 seconds it's going backwards, but after 4 seconds it's going forward. The numbers aren't really important, I mean, kind of. So it's going faster here after 4 seconds than it was going slower after 2 seconds, but they're going opposite directions. So the number represents how fast it's going, of course, but the sign represents the direction that it's going. All right, so now, really when we're asked if it's moving in the positive direction, we're asked to find when is the derivative positive. And we know when the derivative is 0, and in fact, if we were to graph this, notice this is just a facing upward parabola that passes through the t-axis at 3 and 1. So if you graph that, you get something like this. Let me show that in black, just for contrast. And if you wanted to, you can plug in 0, you get 9. So that would pass through the y-axis at 9, or I guess the x-axis at 9, but you get the idea. This is the t-axis, and that's the x-axis, s-axis. So this is the derivative of s prime of t, or let's call it v of t for velocity, but really it's s prime of t. Okay? And we're asked for when it's positive. Now it's positive when t is less than 0, not 0, but when t is less than 1. So in fact, let me shade that. So this is when the velocity is positive, so we have positive values. And here that's also where it's positive. So notice in between 1 and 3 is where it's negative. And yeah, clearly so, because notice at 2 it's negative, so that's going to give you a negative value. But then 4 is after 3, so that's clearly positive. So when is the particle moving in the positive direction? Let me say under 1 second and after 3 seconds. That I think is a valid response. Now, technically you can't have negative time, so really it should be from 0 to 1, but if you say under 1 second, then that kind of implies from 0 to 1 second. And now part E, finally find the acceleration after 4 seconds. Now, I'm going to erase this to show that, but I want to kind of explain something here. Acceleration, if you don't know, is how fast your velocity is changing. It's basically the instantaneous rate of velocity. So the instantaneous rate of s is s prime of s, or s prime of t, I should say, which is velocity. So what acceleration is kind of the next step. It's the second derivative. So if you want to call this, I guess, a of t. So here we really could have called this v of t, kind of like I showed with the graph. But here if we call this a of t, notice that a of t is just s double prime of t. So we can find the second derivative. And that's not too difficult because we have s prime of t right here, so just take its derivative again using the power rule. You get 6t for the first term minus 12. And this is the acceleration. Now, after 4 seconds, just plug in 4. So s prime of 4 is 6 times 4, which is 24, minus 12 is just 12. And that will be in meters per second squared. And I guess we should box these things, but these will be our answers for each of these parts of the problem. That one, this has 2 answers. This is 1 second, 3 seconds, it's under 1 and after 3. And yeah. So that's all I want to say for this example. We're going to move on, but really the next examples we're going to see are just going to be in different topics. The idea is exactly the same though. Rate of change is just derivative. But you have to be particular about what you're taking the derivative with respect to. It better be the variable you have, but what that represents is key. So notice here it's in terms of time. Velocity and acceleration are both rates of change with respect to time. So now let's take a look at some more examples. All right, so here we'll actually take a look at that biology example I was talking about. And really this is an example in a topic known as exponential growth or decay, which is actually the next section, 3.8. So we'll see examples of this in more detail there. But here we're given this scenario, and it's a lot of words. I'll read it to you. So it says, by sampling the population of bacteria in a homogeneous nutrient medium at certain intervals, it is determined that the population doubles every hour. If the initial population is 100 bacteria, find the rate of growth after 4 hours. So the rate of growth is how fast the population is changing with respect to time. And in particular, this kind of tells us that our time is in hours, and it tells us that our population is in bacteria. So our answer will be so many bacteria per hour. Now, how we find that rate of change is just by considering the derivative, but we need a function of population, like actual number of bacteria, in terms of time first, in terms of the variable time. So it's something that we've kind of noticed, is that we're given a certain scenario, basically a formula or a function, then we can find its derivative. Now, like we saw in the last example, we had the function given to us. Here we don't. So here we have to build it up by a few keywords. So first off, we have it doubles every hour. So after 1 hour, it's double what it was. And the initial population is 100. So if we were to build this function, I don't even say what it's called, but if you want to call it f of t, I guess we can call it n of t. Let's call it p of t for population, capital P of t. And I want to figure out what it is, but before we actually build the function, we need to figure out certain values, which isn't difficult to do, given the nature of how it's worded. We can actually figure out certain values after a certain amount of time. In fact, after every hour. So for instance, the initial time after 0 hours is 100 bacteria. So that's the initial time. But then after 1 hour passes, it doubles. After another hour passes, it doubles. After another hour passes, it doubles. So do we notice any relationship between what we're plugging in and what we're getting as a result? Well, maybe it takes some time to actually, sorry, this should be 3, sorry. So after another hour, so 2 plus 1 more hour is 3 hours. So maybe it takes a little bit of time to notice some pattern here, and I'll just kind of tell you what the pattern is. So notice after 1 more hour, it'll yet again double. If you ignore the zeros, the numbers are 1, 2, 4, 8, 16. And notice that's just, you're multiplying by 2 each time, but really these are powers of 2. So really you can write each of these as 100, hence the 2 zeros at the end, times that associated power of 2, depending on the number we're plugging in. So 2 to the 0 is 1, so that checks out. 2 to the 1 is 2, that checks out. 2 to the 2 is 4. 2 to the 3 is 8. And 2 to the 4 is 16. And this goes down indefinitely, meaning that this pattern actually is consistent. So this is just the initial time 100, or initial population, I should say, 100 times 2 to the time, 2 to the t. So now we have this relationship. This is actually a really, 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 really good achievement here. Now we have our function. So this is an example of building a function, and I think we'll do another example where we're not given an actual function and we can try to build it. But now what we want to do, now that we have a function, let's find the rate of growth. Now rate of growth is again dp dt, so it's just the derivative with respect to the variable t. It's in terms of t, so we're good. So p prime of t is, well, let's see. By constant multiple rule, the 100 comes out for free. Derivative of 2 to the t, as we saw in the previous section, is itself like e to the x. Derivative is itself, but you multiply by ln of the base, that's times ln of 2, and then we plug in, well, it's after 4 hours, so after 4 hours now we plug in t equals 4. So when t is equal to 4, we get p prime of 4 is equal to plugging in 4. So that's 100 times, well, 2 to the 4 times ln of 2. And actually we know this is literally just 1600 times ln of 2. And if you use your calculator, you should get about 1109, I think. Right, so using my calculator, it is actually 1109. It rounds to 1109 if you round to the nearest integer. And this is in bacteria per hour. Now, this doesn't mean that it consistently increases by this amount of activity every hour. This just means that this is the rate of change after 4 hours exactly. After 4.5 hours, so half an hour after this, the rate may go down or may go up actually. Kind of depends. So just keep in mind that this is derivative is, in this case, is a function dependent on t. So it's not always going to be this constant rate of change. But again, it just depends on what you're plugging in for t. All right, so that was enough for this example. It's kind of interesting because we can build our own function. So now let's see a few more examples that involve building our own function now. Right, so for these two examples, I'm not writing the topic. They're kind of problems in geometry, which I guess is a natural science. It's a subcategory of math. This one in particular could be written as being the topic of computer science, which is a subtopic, or I guess an applied topic of natural science. So yeah, that I think is okay. But anyways, let's just get to it. So for the first example, it says, find the instantaneous rate of change of the area of a circle with respect to its radius. So it's not how fast the radius is increasing, but it's how fast the radius is increasing in respect to how fast the radius is increasing. So we can actually find that out. Notice that the area of a circle is pi r squared, if you recall that result from geometry. Here we'll recall a different result from geometry. But notice this is indeed a function of r, so we can call it a of r. And now to find the rate of change of the area with respect to the radius, that's dA dr, which notice is just a prime of r. Great. And that is just using the power rule, and that's going to give you 2 pi r, which is actually the same formula as the circumference, and allow you to kind of think about that a little more as far as why that's the case. And notice here there's no units, so I'm not going to worry about units at all. But here, we're going to plug in 2 to find the exact rate of change when the radius is 2. So when r is equal to 2, we get a prime of 2 is 2 pi times 2, which is just 4 pi, and that's the answer, the unitless answer. Here we will have units, but the units get a little funny. In fact, the units get funny here. So in fact, if this was like inches, let's say, then the rate of change of the area would be in inches squared over inch, which would just be in inches anyways, which is kind of weird, but we'll see that here. So here in this example, we say that, or it said, that a cube is being generated by a computer program such that all side lengths are increasing at the same rate. So kind of imagine a cube kind of being constructed, being made. So imagine, I guess I could draw it. I'll just draw it over here. It's fine. So imagine we have this cube being made, but it's being made such that all of the sides are moving at the same rate. So this is changing like that, this is changing like that, and I guess this is changing like this. So it's kind of like spawning from a corner and just slowly creating this cube. So at a given point in time, if you pause the program, it'll be a cube like this, and if you unpause it, it'll keep growing, and then if you pause it after that, it'll be larger. So okay, so we understand what it's trying to say. And now it's just find the rate of change of the volume with respect to a side length. Notice a cube means all the side lengths are the same. So in fact, if you want to call them S, this is an S by S by S cube. Good. With respect to a side length, so the volume with respect to a side length when the sides are each 35 pixels in length. So recall that the volume of a cube is S times S times S, which is S cubed, and notice this is indeed a function in terms of S. We can find its derivative, and that is just going to be, well, the rate of change at which the volume changes with respect to the variable S. So dV ds basically is v prime of S. And notice using the power rule, that's just 3s squared. And now finally plugging in S equals 35 pixels, we get v prime of 35 is equal to 3 times 35 squared, and I'll use my calculator here. Right, so I got 3675. And again, the rate of change is going to be funny because the rate of change is, well, the unit of the rate of change anyways is going to be funny. Because this is the rate of change at which the volume increases with respect to the rate of change, well, the rate of change as the volume increases with respect to a side length. So how fast the volume is increasing with respect to the side length at that given point in time. So it's a little weird, but notice volume is measured in inches, I guess in this case pixels cubed, and the side length is measured in pixels. So it would be pixels cubed over pixels, which is pixels squared. So I'm not going to talk about why the significance of this unit, but at least we kind of have the understanding of how I got that, hopefully. And it's kind of similar to considering volume, not volume, but considering something like velocity, that's what I meant to say. Now velocity is in, let's say, meters per second, like we saw in the first example in this section. And that's because it's distance over time, right? It's the rate of change as distance increases over time with respect to time. The unit for distance is meters in that case, and unit for time is, well, seconds in that case. So meters per second will be the unit. But here, we're not dividing distance by time, we're dividing volume by side length. So the units would then be pixels cubed over pixels, which is just pixels squared. So I'm not going to talk about the significance of what that means too much, but at least we see the process. Now we're going to take a look at one last example, and it's going to be an example in economics, finally. All right, so finally we see an example in the social sciences in economics. So here we're given that a company estimates that cost in dollars of producing X items is given by this, C of X equals this weird function. And companies sometimes actually do this. They figure out a particular function to figure out how much it'll cost them to produce a certain amount of items. And I know that sounds a little funny because you may think it's just a simple thing as far as, well, what are the parts, what's the labor. It can be a little more technical than that at times. These things tend to change, especially like throughout the year. Some products may be in more demand than others as far as materials of creating a certain product, or wages may go up or down, well, usually up. But yeah, so you have certain people in the background creating these kind of things, these kinds of functions anyways. But now let's just carry on with the problem. So it's asking us to find the marginal cost, which, by the way, marginal cost just means instantaneous rate of change with respect to the number of items produced. So instantaneous rate of change of cost, I should say, of cost with respect to the number of items produced. In other words, since X is the number of items produced and C of X is the cost, this is, well, marginal cost is dC over dx, which is just, well, C prime of X. So marginal cost is literally just finding the derivative, which is fine. But then we want to find it at the production level of 500 items, so we'll plug in 500 items. Now we want to compare this to the cost of producing the 501st item. So this is kind of a two-part question. But let's just kind of figure marginal cost first. So remember, marginal cost, from what we just discussed, is just C prime of X. So that's going to be pretty simple. Just apply power rule. Notice 10,000 goes to 0, 5x goes to 5, and then that derivative will be 0.02 times x to the 1. Notice 2 times 0.01 is 0.02. Great. And now we want to figure out what the marginal cost is when x is equal to 500. So this is C prime of 500. So let's see. I don't think this is going to be too difficult because notice 5 times 2, well, it's 500 times 0.2. In fact, something you can kind of figure is that 0.02 is really 2 over 100. Times 500, the zeros cancel, so this is just 10. So in fact, this is 5 plus 10, which is 15. And the unit of marginal cost in this case would be, well, think about it, it's the rate of change of cost with respect to items. So it's going to be the cost unit over the item unit. So this in particular is $15 per item. So this is the answer for actually the first part of the question. And now the second part asks us to compare to the cost of producing the 501st item. Now actually, if you plug in 501 to C, this is not the cost of producing the 501st item, this is the cost of producing 501 items. So this I'll actually use my calculator and let's figure out what this gives us. Okay, so using my calculator, it actually gave me exactly $15,000 and $15.01. Just want to make sure on that. Yep, sounds good. And remember, this is the cost of producing not the 501st item, but 501 items. So how can we find out the cost of producing the 501st item? We'll just take this cost away from producing 500 items. So notice the cost of producing 500 items is plugging in 500 into this this function here. And I've already done that ahead of time. And it actually gave me about, well, exactly $15,000 in those cents. So notice if we actually subtract these, this gives us the cost of producing the 501st item is, well, let me just say equals the difference between these two, which is just $15.01. Now, this isn't really the answer because it asks us to compare these. And notice that the cost of producing the 501st item is approximately C prime of 500. And that will actually always happen provided that the number of items we produce is kind of large compared to just producing one item. The rate of change will actually be approximately producing the next amount. And the reason being is because, well, if you recall what derivative is, C prime of x is, remember, limit as h goes to 0 of C of x plus h minus C of x all over h. And notice, as h goes to 0, this is equal to this, but really this guy here, C of x plus h minus C of x, that's just doing this right here. And since h is going to be 1 in this case, this is actually, well, approximately C of x plus 1 minus C of x. Provided that x in this case is way larger than 1. So in this case, 500 is way larger than 1. And h represents 1 in this case because it's, well, the cost function is kind of funny because you can plug in a decimal amount, for instance. So can you produce 0.5 items? Not really. So for that reason, x plus h, these are all integer values. So h smallest can be 1, even though we're taking the limit here. So marginal cost is kind of a, I don't know, it's a little more figurative or I guess theoretical, but at least the idea still holds. And it is true that the marginal cost is actually equal to the cost of producing the next item in line. Well, approximately anyways. Notice how far off we are just by 1 cent. So this is a good example, I think, of course, in regards to economics. And I hope I did justice of showing you some problems regarding rate of change for natural and social sciences. And I'll see you in the next video for 3.8, where we'll be discussing the exponential growth and decay problems, kind of like we saw with the biology problem here involving bacteria. In fact, they'll all be pretty similar to that, but we'll actually see different types of models, not just the one we saw there. So I'll see you in the video for that. Thanks for watching, and I'll see you then.